300 million tons of salt are produced globally each year. This mass is sufficient to cover the entire Sahara Desert with a layer half a meter thick. At first glance, the product seems like simple, tiny crystals, but in reality, it acts as the chemical foundation of life. One can notice the immense scale of the deposits required to meet this demand. Why is this mineral so vital for biology? The necessity is dictated by strict cellular functions. It maintains water balance, enables nerve transmission, and protects the cells of all living beings. Extraction proceeds from coastal flats to deep underground mines. It is visible how the raw material is harvested before processing. But this is just the beginning. Refining and packaging transform the ore into familiar seasoning and industrial components. The equipment gradually purifies the flow to meet standards. Thus, the material reaches the state ready for the further stage. 70 million tons of salt annually constitute the output of China alone, marking it as the global leader. This figure represents nearly 1/3 of the entire world's supply. How can a single drop of seawater eventually transform into millions of tons of pure crystal? At first glance, the process seems to rely on simple evaporation under the sun, but in reality, it involves a complex synchronization of geology and heavy mechanics. The industry stretches its reach from the expansive fields of Tianjin and Shandong to the coastal islands of Hainan. While 30% of the world's salt is extracted from the ocean, 40% comes from vast underground mines. The mineral has existed alongside humanity for thousands of years, but this is just the beginning. One can notice how the system has become fully mechanized, utilizing automated harvesting to collect the raw mineral. The material enters giant closed-loop refining and drying systems for processing. Alongside this industrial advancement, nature still preserves vibrant natural salt lakes. Because geological formations vary, over 400 of these crystal factories are spread across the continents. Therefore, from South America to Africa and Oceania, these sites attract millions of visitors each year. The focus now returns to the place where the salt is born. 50 degrees Celsius is the extreme temperature the pond floor reaches under the relentless glare of the sun. This intense heat forces 6 to 8 millimeters of water to evaporate from the shallow basins every single day. The process leaves behind delicate layers of salt crystals that cling tightly to the dark bottom like a growing frost. At first, they appear as a barely visible film, but over time, they thicken into a solid, brilliant mass. But this transformation is only the final result of a long and calculated preparation cycle. Workers dredge dense mud and reinforce the perimeter dikes every December to prepare the system for the incoming dry season. Why do engineers line the bottoms with dark cement or tightly compacted clay? At first glance, it seems simple to just prevent the valuable brine from seeping into the earth, but in reality, this choice drives the thermodynamics of the entire process. The dark material maximizes heat absorption, making evaporation occur 2 to 3 times faster than it would on natural soil. One can notice the greenish streams of seawater flooding the network of shallow channels when the sluice gates open. The water enters only when the tide hits its highest point, ensuring a starting salinity of 3 to 5%. It flows into settling ponds where sand, silt, and natural algae slowly sink to the bottom over a period of 24 to 72 hours. A refractometer is used to verify the composition before the valves turn again to release the flow. But this is just the beginning, because the brine must now navigate a precisely calculated sequence of concentration ponds to shed its water content. Therefore, the liquid moves through basins of varying depths and surface areas to gradually increase its density. Under air temperatures exceeding 30 degrees Celsius, the concentration rises steadily from 5% to over 25%. In modern farms, Automatic sensors monitor the water levels by the hour to prevent stagnation. Traditional workers, however, watch the liquid shift color from deep blue to milky white to judge the saturation. It gets more complex further on. The saturated brine is directed into crystallization ponds that are only 3 to 5 centimeters deep to maximize exposure. This shallow depth turns the water surface into a flat mirror that accelerates the final drying process. After nearly 2 months of evaporation, the fields are covered with a shimmering layer of white crystals ready for collection. In regions like India, Vietnam, or Senegal, workers use bamboo rakes and aluminum shovels to gather the harvest manually. They push the salt into cone-shaped mounds over 1 meter high to drain naturally for 24 to 48 hours. Every movement of the shovel must be steady to avoid scratching the delicate pond floor, which could ruin the next cycle. In contrast, modern operations in Tianjin or Australia deploy automatic salt harvesters to handle the load. And this is not the limit. Machines equipped with rotary rakes activate when moisture levels drop below 4%. It is visible how suction conveyors lift the gathered material from long rows directly onto waiting trucks. Each machine processes between 30 and 50 tons per hour, clearing dozens of hectares in a fraction of the time. The massive mountains of salt stand ready against the horizon, awaiting transport to the refining plant. 500 meters straight down is the distance workers travel to begin their shift in the Goderic mine in Canada. Why do engineers extract salt from such deep underground labyrinths when surface fields exist? It would seem easier to simply harvest the mineral under the sun. But in reality, these massive salt cities preserve a resource that has existed since the ancient oceans more than 400 million years ago. This underground network stretches for dozens of kilometers, far removed from the dazzling white fields above. A day in the salt mine does not begin with sunrise, but with a long descent into a silent world without sunlight. 7 million tons of salt are produced here each year, a volume large enough to cover the entire North American highway system during the winter. Workers move through highway-sized tunnels in specialized trucks, traveling between vast chambers carved from the earth. The work truly intensifies when engineers operate continuous miners. One can notice how these massive machines, over 15 meters long, drive their dozens of steel teeth into the solid rock. They cut ceaselessly, releasing hundreds of tons of salt every hour. But this is just the beginning. The stability of the entire operation rests on the room and pillar method. At first glance, leaving enormous pillars of salt standing seems like a loss of valuable material, but in reality, they are deliberately left as natural supports to maintain the geological structure. These pillars form an intricate network of mining tunnels stretching for many kilometers. Once the salt is cut from the walls, it falls to the mine floor in a rough heap. Large bucket loaders or conveyor belts immediately collect the loose material. It is visible how the salt is transferred into underground haul trucks with a capacity of 30 to 40 tons for transport. The vehicles deliver their heavy loads to the primary crusher station located directly within the mine. Here, the large salt blocks are crushed into smaller, uniform pieces measuring 20 to 50 millimeters. This size reduction makes the material significantly easier to transport to the surface. Salt dust is rigorously controlled using a mist spray system, while the entire tunnel network is ventilated under pressure to ensure a safe working environment. It does not end at this stage. After crushing, the salt is transported to the surface using a skip hoist or an inclined conveyor belt. The automated system operates continuously, ensuring a steady flow of salt to enormous dome-shaped storage facilities awaiting above ground. From there, the mineral is either distributed to refining plants or shipped directly for use in road de-icing, chemical production, and food processing industries. the extracted resource is now ready for its final destination. 20,000 tons of weight can be carried by a single shipment bound for destinations around the world. The journey of salt enters the stage of large-scale industrial transportation immediately after harvesting, utilizing massive logistical power. In coastal fields, front loaders and mobile conveyors transfer dried heaps onto heavy-duty trucks or barges with the steady hum of diesel engines. One can notice how the white salt convoys stretching along coastal roads in China, India, and Vietnam create an iconic image of the harvest season. But this is just the beginning. Why is such a complex logistical chain necessary for a simple mineral? It would seem simpler to process everything locally to save on transport costs. But without this industrial network, supply for chemical factories in Europe and snow-covered highways across North America would collapse. Engineers in underground mines like Goddard in Canada or Winsford in the United Kingdom utilize cranes with clamshell buckets to move the rock. Automated conveyors load the raw material onto cargo ships with relentless efficiency, ensuring a continuous supply chain. Once inside modern refining plants, the raw crystals are poured into huge feed hoppers. Vibrating conveyors carry the flow forward, where electromagnetic separators and multi-layer mechanical sieves remove soil, sand, and metal particles. The equipment gradually separates the flow, ensuring only pure crystals remain. It gets more complex further on. Because ordinary water would destroy the product, washing the crystals requires a specific chemical balance. Next, the salt is washed with a saturated brine solution, a globally used technique. At first glance, it seems risky to wash salt with liquid, but in reality, the difference in density removes impurities without dissolving the crystals. The mixture is then centrifuged to remove excess water before entering rotary dryers. Hot air blasts the material at temperatures between 120 and 150 degrees Celsius. This ensures the moisture content drops below 0.5%, making the grains crisp. And this is not the limit. Therefore, the dried salt is crushed and sieved to produce specific industrial and culinary grades. Coarse salt is separated for industrial use, fine salt for food, and ultrafine salt for pharmaceutical applications. Precision mist spraying systems enrich the product with iodine or trace minerals to meet international nutritional standards. However, even in advanced factories, salt remains a silent enemy of machinery, corroding metal faster than almost any other environment, attacking even stainless steel. Everything only gets more complicated. The process transitions to the final stage of manufacturing. From intermediate storage silos, the salt flows through screw conveyors into dosing hoppers, where electronic weight sensors control every gram. Vertical form-fill seal machines, the most common technology, pack between 60 and 100 bags per minute. Weights range from 250 grams to 50 kilograms depending on the production scale. It is visible how the multi-layer polypropylene film wraps the product, providing moisture resistance and traceability via pre-printed QR codes. Small bags are automatically grouped into bundles of 10 to 20 packs for distribution. Large sacks are neatly stacked on wooden pallets and wrapped tightly in polyethylene shrink film before being moved into storage. In large-scale factories in countries like China, India, and Egypt, the entire cycle takes less than 2 minutes. Fully automated PLC control systems and industrial cameras monitor every movement in real time. Transition to the next level. A completely different approach exists in the realm of traditional Asian medicine. Bamboo salt represents an essence of nature combined with meticulous craftsmanship. Unrefined sea salt is tightly packed into mature bamboo tubes aged 3 to 5 years, chosen specifically for their thick walls and resistance to pests. Workers seal both ends with yellow or red clay to prevent leakage during the intense heating process. The tubes are placed in a kiln and fired at high temperatures ranging from 800 to 1,500 degrees Celsius. One can observe how the firing process changes the physical properties of the substance. The firing can be repeated once, 3 times, or even 9 times for maximum effect. During the 9th firing, the salt melts into a solid mass and takes on a distinctive dark purple hue. After cooling naturally, the tubes are broken open to extract the salt, which is then crushed into powder or granules. This salt is considered energetically rich and beneficial to health. Thus, the transformation concludes, leaving the crystal purified by fire or technology, ready for its final purpose.